Right, part two. So what do we have here? So previously in the part one, as a quick recap, it's like a Netflix recap. We talked about the Eady problem with no slope. So now I'm going to put a slope in. So we're just kind of saying, well, what should it do? So the obvious thing is that I should change the CRW mechanism. So I'm going to kind of illustrate what actually happened. So for some context, this is actually, this is part of a submitted paper. So if you're interested, you can have a look at the archive thing for this. So we got the reviews back last Friday, I suppose. And the referee pointed out that there is currently too much stuff going on. It's a bit too much stuff, it's a bit too jumpy. So it's kind of useful for this talk, because it kind of got me thinking about how I should actually do the revision. So the paper really concerns about the linear instability of the modified Eady problem, in this case in the presence of a slope. Okay, so that's what so this is the same stuff. You have so for this problem, we still take a linear shear flow, and you would expect to have your Rossby waves or your PV anomalies at the top and the bottom. So now we're going to put a meridional slope in. And we're going to make the assumption this is essentially linear and is very small relative to the depth, I suppose. So there's some sort of Rossby number assumption about the magnitude of the slope. So the kind of thought experiment you might expect, so it's kind of clear that if you put a slope in, you have to affect the waves. But exactly how do you affect the waves is kind of the thing which is missing, I would say, in the literature. So this would be so this is XZ, this is YZ, so you're looking at the flow head on. So this is flow going into the page, and this is flow going out of the page. The associated buoyancy, isobuoyancy levels are given here, so these are the slopes, essentially. So normally what you would expect is that in the baroclinic instability, you have some sort of disturbance, and that's going to lead to a poleward flux of buoyancy. So you move this tube polewards in some way. So in this particular configuration, the argument is that if you move it to the north or move it to the right, the slope allows you extra stretching. So you are allowed to stretch more relative to the standard case where you do not have a slope. From that point of view, this adds to the PV. So you can imagine in this particular setting, you're really adding some stuff to the bottom PV magnitude. So in the standard Eady case, what you might expect is that the top and the bottom has a similar jump in the PV delta sheet. Now this delta sheet on the bottom is slightly stronger. For this setting, it's slightly stronger. All right. And you can imagine if it's going the other way around, then it's actually counteracting it, so it's less. So the existing arguments, I'm just going to throw this out for completeness. So the existing argument normally is in terms of, again, with CRWs. So the delta, so this would be what's known as a delta less than zero. I'll define what delta means in a bit. This is going to add to the PV. If you add to the background PV, then you're going to make the background PV gradient, because the jump is going to be bigger. The bottom waves are going to go faster. So if these are Rossby waves, then the Rossby waves are magnitude, the amplitude and the phase is going to be dependent on the background vorticity gradient or background PV gradient. So if you increase the gradient, you're going to make the wave faster. So in a particular frame of, like a sensible frame of reference, the phase speed of the relevant phase speed on the bottom is u plus c. The one at the top is u minus c, but this is the one going left. If you increase the background PV gradient, the u plus c has to increase. For phase locking, you want a phase speed matching, so the u minus c has to increase on the top. The problem is that, so your u cannot change. So the only way for this to increase is if your C is going to decrease. If these are Rossby waves, then the C is going to go like 1 over k, the wave number. So what you want is you want a larger k. So the presence of a slope you would expect to drive the most unstable mode to the larger wave number. So
can I just get you to clarify the diagram a little bit? I mean, your red and green sinusoids are going into the page, right?
Yes.
They're going into the page, and that direction's the same as the left-right direction on your other diagram, right? Okay, thanks.
So that's, I guess for schematic reasons, that's a little bit difficult to draw this. So I probably should have drawn it here, I suppose. Yeah. Okay, so that's if you were purely talking about phase speed matching, and this would be the argument you would get. So that's in this paper. So from a propaganda point of view, hopefully, I hope you really did not like this argument, but I don't. So I'm going to give you what I would argue is that this argument is incomplete. So I'm going to give you what I think is really what's happening. So the current state is that, so most people observe that if you have a slope, then you have to modify these kind of wave interaction, but they don't exactly say why, kind of for 10 years or so. So this paper says why. Or at least we give what we think is actually going on and back it with analysis. Okay, second part. So in the standard Eady, second observation. So the standard Eady model with the no slope. So is in the 2D problem where you have no meridional wave number. So normally what we do, what is shown. So this is something like what you would find in a standard classical GFD book. So it's like what you would find in Thales. You tend to show the normal mode stream function, and you find that this leans into the shear. So the argument when we talk about CRW is that your PV structure should lean into the shear. Stream function and PV are related by second order derivatives. So so second order derivatives normally give you is a negative definite operator normally. So what you would expect is that if you plot the PVs, then you would flip the sign, but your tilting is still into the shear. And you get this pi by 2, which is from the kinematic argument, that might be what you expect of the maximum growth. So the question here is, does this tilt depend on delta? And a more fundamental question is this even the right thing to look at? So I always found it weird personally that we talk about, a lot of the literature talks about the counterpropaggation Rossby edge waves, which are defined in terms of PV, but we never show the PV. This is the stream function, which is not quite the PV. It's related to PV, but it's not quite the PV. So what happens if you actually look into the edge waves themselves? So the mathematical problem here is you've got something which is a superposition of edge waves. So somehow you want to find the right basis for it. So that's another way to look at it. Okay. So let's do the mathematics of it. So you start again with linear QG. So I'm going to make the assumption that the slope is essentially small, specifically at order Rossby. So it doesn't intrude into the interior, but it comes in at the boundary condition. So the only thing I change is the boundary condition. So this is like an extra W. Okay, so that's otherwise everything's exactly the same as before, except this little bottom bit. You non-dimensionalize as useful, and you get this delta parameter coming out. F is still exactly the same as before. It's the inverse Berger number. So the key parameter here would be your delta. So delta measures the orientation between your slope and your slopes. So if you have something which is like a slope tilting this way and your isopycnal slopes or your buoyancy slopes are intersecting this way, then this is a negative delta. The positive delta would be this one. So the way I'm thinking is I have somehow, by hand of God, I can move my topography around, but I'm keeping my isopycnals exactly the same. You can do it the other way around, doesn't matter. So delta is usually sometimes in the literature, sometimes this is called prograde or retrograde configuration. I don't use that because that's confusing to me. I just talk about delta positive and negative. All right. The solutions are exactly the same before, but the interior hasn't been modified. So you still get Sanj and Koch. The A and B, you still need to fix by the boundary condition. If you do this, then you get a slightly different dispersion relation. In the delta equals 0 regime, you get exactly the standard Eady model coming back. So this includes the standard Eady model. And then you can solve this analytically or numerically, it doesn't really matter. So the instability characteristics would be, so here I take the L equals 0 case, because the L equals 0 case, the meridional wave number 0 is normally the most unstable mode. So to clarify a point which was raised earlier, so I'm assuming 2D, but it's really uniform in Y. So there is really a third direction, it just happens to be uniform. Okay, so here the things I can choose, the things I have freedom to choose is my zonal wave number and my delta. Okay, and these are the corresponding CRs and growth rates and your phase speeds for positive delta, 0 delta, and negative delta. So this is your standard Eady problem. All right. So the previous assumption about the previous explanation about phase speed matching works for negative delta. because you are, so the green line here is the line of maximum growth rate at fixed delta. So the maximum growth rate is certainly tending to larger k as you go to the negative delta. But I would argue that phase matching condition, at least that argument is incomplete because it doesn't work for the other way around. The other thing is it doesn't really explain why your instability is, your growth rates are decreasing as you go into this particular regime. It doesn't have to, but it is. There's some PT symmetry stuff to do with, so both of you have talked about. So you can show that the modified Eady problem is also PT symmetric. So that's why you have these kind of, these regions, exactly where you have regions of instability are where you have a phase coalescence or like a mode coalescence. All right. Okay, so that's what's observed. So the current state is that the explanation for delta negative seems to be okay, but it doesn't extend to the other the positive delta case. It doesn't necessarily explain why the growth rate is like this over parameter space. So that's what we're going to try and do. All right. So let's go back to the first problem of this one. So this is looking at an eigenfunction, but as I mentioned before, is eigenfunction really the best thing to look at? If we talk about edge waves, maybe we should just actually look at the edge waves. So the mathematical problem is that this is a superposition of two things. So you somehow want to define an appropriate psi t and psi b such that the linear superposition is this guy. The problem, of course, is this is ill-defined, right? You need to give it some constraints, but otherwise I could say whatever the hell I like. And this would be valid as long as it sums up to this. So the observation here is that the tilt in the eigenfunction is pi by 2, but if you do it in terms of a sensible edge wave basis, is that necessarily pi by 2? All right. So the way you would do this is that suppose you have a linear combination of the two in the stream function. Then because your potential vorticity and your stream function are related by a linear operator, at least in the modal regime, then you have an analogous PV top and PV bottom. So I'm going to start with this guy. So these things are related by a second order differential operator. It's a Helmholtz operator with some boundary conditions. So in this case, what I'm going to make the assumption is that the bottom edge wave has no PV anomaly or buoyancy anomaly at the top, and the top one has no signature at the bottom. Okay, so that's actually somewhat related to what Davies and Bishop did in '94, but they did it in terms of buoyancy. Okay, so the edge waves in this case are localized on the top and the bottom, and it does not induce another PV or buoyancy anomaly at the other edges, at the other edge waves. If it's sufficiently localized, etc., then what I can do is I can model this as a delta function. It's really a delta distribution. So formally, you should really be thinking that there's lots of integrals going on here. So what I would do is I take my structure, I assume the bottom is localized at the -1, z -1, and my top one is localized at z +1. I allow, in this case, for a time variation. So this is going to be my wave part. This is my spatial localization part. If you take this delta and put it back into here, then what you really have is a Green's function problem. And in this case, you either look up the Green's function, or you can compute it yourself, or you can construct it manually. It turns out it's Cauchy-Sange. So with this, you can think of this as a formal inversion of a delta function into the stream function. So there is an operator relating the psi to the q. I have q, but I want psi, so I want to do this operator to the -1. So it's a bit like, so the Green's function is a bit like the formal inverse of the operator, and it's given, in this case, given by this guy. The main thing to notice is that these are exponentials, essentially. So it's written in Cauchy-Sange, but it's really decaying exponentials. So what you're saying is that at the influence at of the bottom edge wave is maximum at the bottom, but it decays exponentially as you go towards the other edge, and it's such that it vanishes at the other edge. Well, but some of the signature vanishes at the other edge. All right. So now you have this stream function. You can put this back into the equations of motion. So there's a lot of tedious algebra which I skip. So what you're going to do is you're going to take this psi b and psi t. This is your psi. So you're going to expand your previous equation in the stream function in psi t and psi b. So now the things you have is qb and qt hat. This is a function of time. If you're going to make some wave-like assumption, then you're going to take that to be a function t as a function of t, and the epsilon t is a function of t. So your phase and your amplitude is going to be a function of t. Analogously for the bottom, so previously, and then you shove it into the boundary condition, and that's what you're going to do. You get 4 equations coming out of this. So somehow I've turned the simple problem with 2 equations into a harder problem in 4 equations. But in this case, in terms of the, explicitly in terms of the edge wave amplitudes and the edge wave phases. And the quantity I would be specifically interested in is the edge wave phase shift. So this is your delta epsilon. And I've defined this in such that your positive shift in this case means the top lags the bottom in the PV signature. All right. So what I would expect is that if I get an instability, then my delta epsilon has to be positive. Because otherwise you don't have a tilt into the shape. So you can say, okay, so one of the things you get out of this is that this is a 4-dimensional dynamical system and it's ordinary differential equations. But this is in contrast to the 2-dimensional algebraic equation. So why would I do this? I'm making it more complicated. So the trick you notice is that there is an extra degree of freedom. So you don't really care about T or B. You only care about T over B. And you don't really care about these individual epsilon t's or epsilon b's. The only thing you end up caring is actually the phase shift. Because in the linear instability, you're free to specify the initial condition. So what that means is you can rewrite your equations, your amplitude phase equations in terms of amplitude ratio and phase shift. So this is now given by, there's a whole load of nonlinear terms floating around, I suppose. So that's where maybe the nonlinear interaction will come through. But the thing with this is that this is a 2-dimensional dynamical system. This is 2-dimensional ODEs. It's a 2-dimensional dynamical system. You can draw your phase diagrams and you can classify everything by your by essentially your equilibrium points and your bifurcations. So you can analyze the phase portraits. You can get synchronized growth by looking at where the fixed points of the systems are. You can look at half bifurcations. In this case, I think it's like a Hopf bifurcation. If you do this for different values of delta, they can plot out the phase portraits of all of these guys, and they look something like this. So here what I have is I got an amplitude ratio normalized by pi, and the delta epsilon, which is normalized by pi as well. So this is pi by 4 I've marked on. And then for 3 cases where we have instability, so this would be your delta positive, delta negative, and delta positive, 0, and negative. So this is the standard Eady problem. Okay, the circular points are the fixed points. So these are fixed points of the dynamical system, and these correspond to the unstable mode. All right. So the way you think about this is that you arbitrarily start with some edge waves. If you leave it long enough, it's going to be the unstable mode that ends up dominating everything. So that is the fixed point you get to. So the fixed point is this circular, and this is the corresponding stable mode. So there's some arguments that these transitions give you the algebraic growth and the transient growth. So in some ways, we get more information by looking at the amplitude phase diagram. I'm not going to talk about transient growth. In the standard Eady problem, so gamma is defined by arctan T over B. In the standard Eady problem, this is pi by 4. So this is pi by 4 when T over B is 1. So this is telling you that in the standard Eady problem, your top and the bottom wave are symmetric. They have the same amplitude. We argued previously in the negative delta case, you are strengthening your bottom, adding to the bottom wave, so you're making the bottom wave stronger. So here what we have is we have gamma, which is less than pi by 4, which is here. If it's less than pi by 4, then it means that this thing is less than 1, so this is a sign error. So B is bigger than T in this point, so this is a typo. And vice versa for the delta case, you should have a T over B. So in the delta case, delta negative case, your bottom wave is stronger. In the delta positive case, your bottom wave is weaker because of this topographic effect. And in fact, you can show for synchronized growth, if you go back to the previous equation, then for these fixed points, then you have to have this relation. So your ratios have to depend on 1 over delta. And the main thing is that this has no dependence on K. It doesn't care about the wave number. It only cares about the background PV gradient, which is exactly it's kind of what you expect. The main punchline is that this is not pi by 2. So pi by 2 is here, is 0.5. So in the Eady problem, that's not pi by 2. The phase shift is not pi by 2. In the delta negative and positive case, these are not pi by 2. And if I do this over parameter space, you can find that it's never pi by 2. So pi by 2 in this case seems to have absolutely nothing. So in the edge wave case, you don't seem to get pi by 2, even though the kinematic argument tells you you should get pi by 2. So what's going on is there are in fact some sort of inconsistency. And previously, when we took the superposition of these two, we get pi by 2. So somehow now we don't. What's going on? In fact, there is no contradiction, or there is no inconsistency. So psi t and psi b in this case are now I've decomposed it into the edge wave structure, which I've subject to some conditions. I would take the most unstable mode, which has, in this case, the phase shift of a little bit, something bigger than pi by 2. I add them together, and you happen to get pi by 2. All right. And the reason for this is that it's a little bit unclear. So I think it's a fluke. My co-authors think there is actually something deeper behind this. For now, I'm just going to leave it as an observation. Generically, for CRWs, you do not get the pi by 2. It happens in the Eady case that you somehow, when you add them together, you get this theoretical pi by 2. So I say that because if you don't, it's just, this is kind of a specific case for the Eady problem. If you generally look at shear instability problems, the edge waves do not have a phase shift of pi by 2. MHD case, stratified shear instabilities, incompressible instabilities, it's not pi by 2 that you care about. The need is slightly bigger, is always slightly bigger than pi by 2. So one possible argument is that you care about mutual interaction, right? So pi by 2 is optimal for constructive interference instantaneously. But if you want to talk about continual growth, that's not, so there are two bits, right? You want the phase shift which enables you to have phase locking. And you want the phase, yeah, so that's right. You want the interaction such that you maintain phase locking and also have growth. So in that sense, the two things are not really separate. You can't tune the phase shift and the interaction separately. They are part and parcel of the same things. So it's really a joint optimization type problem. So from that point of view, it's usually what you need is you need something which is in what's known as the hindering regime. So the two waves need to hinder each other. It's not quite the instantaneous maximum growth, but it is the largest sustained growth, it would seem, and it's not pi by 2. So the thing we make it's a kind of in some ways you can say, who cares, right? It's a small deal. But this is what you tend to find in standard textbooks, and we're arguing, really is actually this thing which is relevant. This could just be I would say this is a little misleading, possibly a little misleading. So maybe don't pay too much attention to that pi by 2. All right. So then a few things just to check consistency. So you can say, well, I do this in edge waves. How does that compare to my stream function, etc.? So the first thing I would show here is the amplitude ratio over parameter space and the phase shift over parameter space. So as expected, my gamma here has to depend on square root 1 over delta. If I work out the amplitude, so this one I'll work out the amplitude ratio. And this really corresponds to the analytical solution. The delta epsilon corresponds to the CRW mechanism in that if you go to long waves, your waves are too fast. Then there's a lot of hindering. On the other hand, if you go to shorter waves, then these are too slow. So you need somehow to have the waves which are helping each other to put it back into the phase locking position. All right. So you get these phase shifts, and so I'm going to skip this bit for now. If you do the analogous thing for the stream functions, you can take the stream function eigenfunction, you take the top and the bottom maximum minimum, and then compute the phase shift numerically. What you have is in the standard Eady case, you get it so happens in the standard Eady case, you get a symmetric interaction. But if you do it over parameter space, there is a hint of this is actually doing what you expect it to do. Because your delta is changing your bottom wave. But the argument should not have a K, the argument we gave should not have a K dependence, but there seems to be a K dependence here. So this gives you a hint of something that is consistent, but is not exactly consistent with their theoretical expectations. The delta epsilon, in this case, the phase tilt doesn't really make sense. There is no correlation really between the two. So I'm arguing that this is not really the relevant thing to look at. Just don't look at it. All right. There's some talk on whether this is really, you can use this delta epsilon, the phase tilt, as an efficiency for APE extraction, and I am fairly dubious whether that's actually going to work. So at least the things I looked at does not suggest that this is in fact what's going on. All right, so the updated, so let me give you an overview of how I think, or what I think is actually going on in terms of edge waves, what is the slope doing? So the key one is this one. If you understand this one, I think the other ones are okay. If you have a delta negative case, you are increasing the background PV gradient on the bottom. You strengthen the wave, so you make the wave faster, but you also make the interaction stronger. All right. So what this is going to do is your bottom wave is going to dominate over the top somewhat. So you can imagine this is going to start dragging this wave with it. So this wave is going to propagate to the right, and it's going to drag the top with it. So the implied CR would be positive, and it turns out that's true. But then your configuration is no longer optimal, so you need to somehow shift this. So one thing you would notice is that your increases in the interaction from the bottom via delta could be offset by changing your K, because K is your wave number. So that so if you remember, I had the flick back a few slides. So the interaction is related to the Green's function, which is a Cauchy Lagrange. These are essentially exponentials of K. So if my K is smaller, then I make this interaction smaller. So I can offset the increases in interaction of the bottom wave by going to larger K, which means that I decay a lot faster. And it seems in this case you can always do it, because I can arbitrarily make this as large as I like, but I can always offset it by making my K as big as I like, within reason. I say within reason, in the sense that I can still get optimum, I can still get a phase locking going on. The problem, of course, is that if you make your K bigger, you make the interaction weaker, then so you can offset the bottom on the top, but then you end up killing the top on the bottom. So the top thing doesn't actually give you that much influence on the bottom. So the mutual interaction is weakened, and then the growth rate has to be decreased. So that explains in this case, at least I think it's an internal consistent explanation for, in the delta less than 0, you should have your most unstable mode going to the larger Ks, and your growth rate has to decrease, because you're killing the interaction arising from this. In the delta 0 case, you have a symmetric interaction, so more or less exactly as before. In the delta positive but less than 1 case, for this Eady problem, so bigger than 1, you have no instability. You weaken the bottom wave, and you would expect the top wave in this case to drag the bottom wave, so your CR might be negative, and it turns out that's true. You can think about playing the same game, right? So in the top case, I make it arbitrarily big, so I offset it by increasing my K. Then I can do the reverse. If I make this weak, then I can decrease my K. I can decrease my K and increase my interaction. Problem, of course, is now if you make your K smaller, then these are Rossby waves, right? So the phase speed is going to be too fast, and eventually comes a point where your K is too small and your waves are too fast, then there is no longer phase locking possible. So you can't arbitrarily go to small K. You can arbitrarily go to larger K in the delta negative case, but in the positive case, you cannot do that because of this additional constraint on the phase speed. In the delta positive 1 case, then you no longer have counterpropagation, so there is no instability, because your PV gradient essentially is reversed. Yeah. So say that again. Because you can always make this, so you can make this arbitrarily fast, and this can always drag this along. But you can always offset it by increasing your K. You can't do that here, so there's asymmetry in this problem. So in this case, if you make your K too small, then this interaction is too, so the intrinsic propagation is too fast to the point where your mean flow is no longer helping you. Whereas in this one, it doesn't matter. You can just make, this one essentially dominates, and this is dragging everything with it. Okay. Then the PV reversal, the Chinese Stern-Pedlowski condition no longer holds, and there's nothing. All right, so I'm going to skip this bit. This is geometric. So I'm going to stop a bit sooner. So I'm just going to summarize. So here I presented I guess, an edge wave basis equivalent. So, so the thing I should say that this is essentially equivalent formulation of the Eady problem, except I just use a different basis. I would argue is a slightly more physically relevant basis. It's entirely equivalent, but it gives you more information. It also gives you a link with dynamical systems, so that's kind of interesting. So most works currently talk about edge wave phase shifts, but then they present the results for. And I'm arguing if you talk about edge wave phase shifts, you should really be presenting edge waves. All right. In this case, I constructed the amplitude phase equations manually, but in general, you can do this in a more general case. So in the Eady problem, you know exactly where the edge waves are. There are cases where you do not know this. So for example, the Charney problem, you don't necessarily know where the critical layer is going to be. But you can define this more generally using what's known as orthogonality conditions. So in this one, what I'm saying is that it's orthogonal in the sense that my bottom wave has no signature on the top and my top wave has no signature on the bottom in the PV sense. You can do something similar by essentially imposing pseudo-momentum or pseudo-energy orthogonality. You can do that as well. And so there's machinery to do this. In the case of where CRW is not defined, there are still ways to define CRW. Up to an approximation. So in this case, I can reduce it down to a finite dimensional dynamical system, and it turns out, again, if you, the thing I highlighted is that there seems to be a link between PD symmetry and instability, and there's a link between instability and CRWs. So somehow there is this kind of triangle of relations that maybe knowing one gives you some information about the other. If one problem is hard in one view, then you just shift another view, and maybe there's another way to look at the same problem. Okay. The thing I did not talk about is this geometric formulation. So it turns out that there's a parametrization formalism called geometric. Normally, it's used from so from a parametrization point of view, we just say it's something. You can use this from a diagnostic point of view. It's not necessarily predictive. But the thing we find in this work, which I didn't talk about, is that the geometric formulation seems to also have relations to the CRW quantities. Particularly the phase angle, the tilt angle is related to the phase tilt, but not to the, the phase angle, the vertical tilt in geometric is related to the edge wave phase shift, but it's not to do with the phase tilt. It's got nothing to do with the phase tilt. So then that gives you extra, I guess, like a square link, right? You got PD symmetry, you got instability, you got CRWs and geometric. Somehow all of these are linked. There's a plausible correlation going on. So maybe there is actually a more fundamental link going on underneath. And the other one of interest is that when you do geometric, it makes no reference to dynamics. But somehow there is a link with dynamics. So you could maybe say that in the case where you do not CRWs, maybe you can use geometric instead. Or another way is that if geometric is diagnostic, then if you have a reduced equation for CRWs, then you can use that to tell you what the geometric quantity should be. So there's like a two-way street. So links are kind of useful because then non-trivial links are useful. But sometimes problems are hard, so you just change the point of view of your problem and do it in somewhere else. So there's a possibility of this being parametrizable, and so this work has looked at it a little bit. Let's say, I think I'll just leave this up for discussion, but the thing that I got interested really for this work is that, so the Eady problem is PD symmetric, and if you were to use kind of a crude argument, then several others are obviously PD symmetric or there are some sort of discrete symmetries in the system. So it's been shown, for example, the Kelvin-Helmholtz problem is PD symmetric. You can kind of see, right, because so you have a flow, you flip the space, but you flip the time, so then your flow doesn't change. So from that point of view, it's kind of obvious. This paper looks at the Phillips problem and really sets out a lot of the terminology and the tools that I've implicitly employed in this work. Other cases, things like Eady with beta, the Rayleigh problem, MHD and the MHD case, you have to be a little bit careful about the extra coordinate, but there is still going to be some sort of parity time symmetry going on with these things. And more generally, these are governed by what's called non-Hermitian operators. So non-Hermitian operators are kind of annoying to deal with because there's not that many stability conditions you can say. Hermitian operators are very easy. So if you talk about things like convection, so I know some people do convection. There is this thing called the energy method. So the energy method relies on the fact that you have a self-adjoint operator. So the energy method does not work for shear instabilities because it's not Hermitian. But the idea is that if this really has if these are governed by non-Hermitian operators, then there's a lot of work which is done in quantum field theory to tell you when there are certain conditions when you have, you can say something about the underlying operator. Maybe that translates to stability conditions in the classical sense. So that's where I got really interested in this stuff. And then there are some papers, there's a recent preprint which puts the PD symmetry link with the CRW. So the CRW equations in the most general sense, from the pseudo-momentum and pseudo-energy orthogonality point of view, is also PD symmetric. And then another possible link is that if you want to derive stability conditions, can you start from the CRW point of view as well? So normally when you derive stability conditions, you start with the maths and then you do some stuff and you get a condition. Can you flip it around to say, if you think CRWs are the building blocks of your instability, when do you get this counterpropagation or phase locking? And from that, can you imply a stability condition that's more general, for example? One of my interests since the PhD is really on these Arnold stabilities. So that's where I got revisited these things. Okay, I'll leave this cat up again. This was in TR 181. So I'm going to stop here, and I'm happy to discuss and kind of talk about stuff. So I have to show this cat because
Okay, so lots of times for questions. I'll start out, but we'll start out with students, but except for one quick one. What's the cat's name?
This would be Mithrandir.
Mithrandir, okay.
Yeah, it's from Lord of the Rings. It's the grey. Is Gandalf? Or is it grey? So we call him Miffy.
Okay, so we need some student volunteers for questions, I guess. Well, I'll ask one while we're waiting, I guess. For the waves and the pi over 2 and all that, right? The linear waves in the regime where there is no growth and there's propagation, right? The linear waves, do they really correspond to the top trapped only signal and the bottom trapped only signal? In other words, there's the two edge waves where if you look at only the potential vorticity or the buoyancy gradient on the top and totally ignore the bottom, the topography, and you get an edge wave that has a signature on the bottom, and similarly for the, vice versa. But the linear waves are presumably a linear combination of those two, not just the, top only and bottom only. And so does that help explain the departures from this pi over 2 phase shift?
The short answer is I don't know. I haven't really thought about it that way. So that's something that we can discuss more, I think. I suppose that's something that the referee picked up and I don't really know how to answer it. So please ask some questions because that might help me do my paper reviews over the next 2 to 3 months.
Go over the mechanism for phase locking again, because that's really the vaguest part of the talk for me so far. How exactly do those waves get phase locked?
So in a frame, I suppose you have to choose a frame first. So let's go back to there. Oops. Where do we start? Where would we go? Let's take this one. Let's just take this one. So what we're going to do is you're going to make the assumption that you're in the frame where this is 0. So in this frame, what you want is somehow you want this thing to not be propagating, I suppose. So this has an intrinsic propagation to the left, but because this is going to be moved by the flow, so there is a net, net velocity. So just by the flow, then this would have u minus c, but then there is an induced velocity from the bottom to the top, which also contributes to this thing. So the phase locking would be, in this case, is the net propagation of the wave, by the intrinsic part, by the contribution from the mean part, and also from the other wave part, is that in fact, is not necessarily 0, but is it maintaining the same phase shift relative between the two waves, and vice versa from the bottom.
This mechanism, would it have worked in the case where you had like the uniform, linear, uniform sort of setup?
Yes, right. Let me draw it on here. I'm very impressed with all the blackboards I made. It reminds me very much of the Newton Institute. I love drawing on blackboards. So what you would have is in the, so I think Akash is talking about this one. So your flow is going this way. So the 0 point is here. So what you would have is you have a wave which is going like this, right? But you have to remember that the U bar is this one. So there's a U bar, but then your U minus C, I guess your U minus C is going this way. So the intrinsic, or rather the C in this case is negative. Right? So it's U minus C and then the whatever extra bit you get from the bottom wave added together. Is that keeping, so in the, is there a frame where this is in fact, both of these are 0, they don't have a net propagation, would be phase locking. Yep. Review articles for learning these in detail, non-Hermitian methods in classical systems. Good question. So the one so this is fairly new. So the person I think who has, so there is a book on this. It's called PT Symmetry. So it's by, so nominally it's by, what was his name? Carl Bender. So if you know your engineering book, there's the Bender and Orszag. So it's that Bender. Carl Bender has written a book on this. He's the lead author, but then, so all the chapters are actually contributed chapters. So people care about it in quantum mechanics because the PT symmetry can have a real spectrum. So normally when you talk about quantum mechanics, you want things to be observable. So the energy is your eigenvalue and you want that to be real. But that's quite restrictive, and it turns out PT symmetric operators could also have a real spectrum, and so that could, in principle, describe physical systems. So people have been looking at this in things like lasers, for example. So there is a review book of sorts on, I wouldn't recommend buying it because it's quite expensive. So there, I don't know how to say this. So there are places online which, violate copyrights and they have freely uploaded PDFs and what have you. Obviously, I don't recommend you looking at those, but if you were to end up stumbling on them, these sites exist. So whether you look at them or not is kind of up to you. You can have a look at those. So there's the book on that. So it's mostly focused on the quantum case, but there are a few systems where they highlight in the classical sense that are PT symmetric. For example, one problem with what's known as the foxes and rabbit problem, so the Locker-Volterra problem. So that turns out to be PT symmetric as well. So it has these periodic orbits. So that would be the first place I would suggest. It's continually being developed, so it's a little bit difficult. So I think that would, for the PT symmetry, that's the first bit. That would be the most up-to-date one, I would say. The older papers by Shepard, so Ted Shepard in the 90s has done a lot on these Hamiltonian stuff, called stability conditions. The papers are kind of hard to get, but if you can find the conference papers, there was one particularly by, I think, celebrating the life of Pedro Reaper. If you can get access to that one I think is the best from a pedagogical point of view. But it's very difficult to find. If you can find it, please let me know, because I've lost my own copy of it.
Can we go back to the parametrization? You brought in GM parametrization in the first part. How do these edge waves and their interactions change the parametrizations? Do you have insights on changing the parametrization or modifying them?
Not at the moment, essentially. Wait, let me, let's have a think. Do I have any insights or whatever? So I'm going to show some disgusting math. Quick recap, just a very brief recap. So there's this, so the Eady forcings are related to this Eliason-Palm flux tensor, essentially. So what you want to do is you want to parameterize these blocks. So essentially what you do is you rephrase some of this geometric stuff into geometric parameters to do anisotropy, to do angles, and to do some energy ratios. The CRW things in the barotropic case, there's a paper by Talia Tamarin she led in 2016. So that's a ridiculous paper, but I'll give you a background to it. So Talia is awesome. So she was doing a master's and she spent, I think, a month or two in Oxford, and then she got this giant paper, which I would easily make out to be half a thesis, half a PhD thesis. So in her paper, what she finds is that in the barotropic shear instability case, there is an explicit relation with gamma m and phi m with the phase shifts. So this is an exact, well, at least in a representative instability problem. I think this is the triangular jet. You can show that exactly, that there is an explicit link between the two. For this problem, what we've done is that we've shown that there is a relation of the phase, there's a correlation of the phase shift with the thing which I did not define. There's a psi t. So phi t you can kind of well, I mean, so schematically you can see maybe there is a relation to do this, right? So you have a wave. So your eddies are tilting this way. So this would be like, so you can think of this kind of tilt to be phi t, but that's probably related to this kind of length delta epsilon. So there is a suggestive link where, so I haven't demonstrated it explicitly, but there is, I mean, from this kind of pictorial point of view, that's maybe what you expect. Delta epsilon is roughly 2 times the phi t is 2 times the delta epsilon or something like this. Exactly how this might work is that your phi t would probably be playing, informing this alpha, which is like an eddy efficiency. So you could, in principle, do something, I'm just talking out loud here. You could, I suppose, do something like a linear stability analysis. And then from that, get your phi t. Use your phi t to tell you what your delta epsilon is. And then, use your CRW, get your delta epsilon. That tells you your phi t and similar quantities, and bung that into this alpha. Alpha, let's go back. So alpha is related to the Jen-McWilliams parameter in this way. So there is a non-dimensional fudge parameter here. So that, in principle, that is something you could do, I suppose, using a CRW mechanism to tell you geometric parameters and use that to tell you, in turn, what your kappa GM might be. This one we haven't really thought about too much. We did it very empirically, but not from a prognostic point of view. Citation and papers. I can send this. I can upload the slides. That's not a problem.
Okay. Yeah. So then we will collect relevant papers and books and put them somewhere for everybody to look at.
Are there any other questions? So maybe I have one. When you added the topography, I guess the idea is W at the bottom is kind of V dH dy, where, you know, if the topography slopes up and you're going to the north, then you're going up. And so there's a Wn squared term in the buoyancy, just like there's a V d by dy of buoyancy. So that's sort of the connection, right? And I guess, so like you said, you know, you can combine those two, the buoyancy gradient and the topography gradient, to give you a sort of a delta function, PV at the top and the bottom. So the one that's depending on which way the topography slopes, basically you're just making the Podolsky condition, the condition that the PV gradient at the top and the bottom be different. Is sort of vanishing, right? In one case, and it's exacerbating in the other. Is that right?
Yeah. So in the, I shouldn't have turned it off. So in the, let's have a look. So this would be your PV reinforcing, and then this would be standard. And then you can only tilt up so much before you kill everything. There's no longer reversal in the PV gradient.
Right,
So
okay.
you kill the...
And can you get that with a non-uniform stratification? I mean, you wouldn't get the nice hyperbolic sines and cosines, but you would get, would there be a different PV gradient at the top and the bottom for non...
But I would suspect, I seem to remember there's a special solution by Linson in the 70s where he considers non-uniform N, which is Eady-like. So I guess we could probably have a look into that. At the top of my head, I don't know, but it's probably doable.
Okay, maybe last call for questions, is there? Oh.
Can you... Yes, so if you look back in the, it's not dissipation as, I guess dissipation will work, right? So as David said, it's going to change the W in some way. So if you look, for example, in the Chen et al. Paper that I cite in the slides, so what they talk additionally about is some sort of Ekman forcing. So there's some sort of Ekman layer at the bottom, and that gives you that extra W, I suppose, and then that would add to your PV as well. So I would recommend you have a look at the Chen et al. Paper. So even though I criticize that paper from the linear stability point of view, I mean, that's just a small part of the paper. The nonlinear, they do a lot more than what I talked about. So the Ekman stuff would be relevant for that dissipation or the frictional effect. Can we share them in chat? Well, how about we share them afterwards as a big document or some, there's going to be we pass the paper around for references and what. We do that instead, however. There's 2 new messages.
So maybe we can just take 5 minutes to stretch our legs before the next talk and get back at 12.